Section: Introduction. In this section, we delve into the fascinating world of large language models, LLMs, and their capabilities in handling various reasoning tasks. We've observed that these advanced models have achieved, and in some cases even surpassed, human levels of performance in areas such as solving STEM problems and generating code. However, it's not all smooth sailing. Recent studies have highlighted that LLMs can exhibit failure modes similar to human cognitive biases. For instance, they struggle with the reversal curse, where if trained on the concept that A leads to B, they might not correctly infer that B leads to A. Another notable issue is distractibility, where the inclusion of irrelevant information significantly hampers the LLM's performance. Our exploration focuses on how the order in which premises are presented affects the reasoning capabilities of LLMs. In deductive reasoning, the sequence of premises should theoretically not influence the outcome. To illustrate, consider a simple logical sequence. If A is true, then B is true. If B is true, then C is true, and A is indeed true. From this, we can deduce that C must be true, regardless of the order in which these premises are presented. While previous research indicates that humans have a preference for certain orders of premises to aid their reasoning, such preferences don't drastically impact their performance, especially in straightforward cases involving modus ponens, which is the logical argument that if P implies Q and P is true, then Q must also be true. Contrary to humans, we find that the order of premises significantly affects the reasoning performance of LLMs. They perform best when the premises are arranged in the same sequence as in the correct proof. For example, presenting if A then B before if B then C generally results in higher accuracy than the reverse order, and this gap widens as the number of premises increases. This preference seems to mirror human reasoning, where processing information step by step without having to jump back and forth between premises is more efficient. We conducted a systematic study using state-of-the-art LLMs, such as GPT-4 Turbo, GPT 3.5 Turbo, PaLM 2L, and Gemini Pro, focusing on deductive reasoning tasks that involve modus ponens. Our findings reveal that rearranging the premises can lead to more than a 30% drop in accuracy. This effect is even more pronounced when irrelevant premises are included. Interestingly, while all models performed best when the premise order matched the ground truth proof, they showed different preferences for other arrangements. For instance, GPT-4 Turbo and GPT 3.5 Turbo generally did better when the premises were in the exact reverse order of the ground truth, which suggests they might be leveraging backward chaining. On the other hand, PaLM 2L struggled with this reversed order. Beyond logical reasoning, we also explored the impact of premise order on mathematical reasoning by modifying the order of sentences in problem descriptions from a subset of GSM-8K experiments. Our experiments confirmed that performance drops significantly, especially for longer problems requiring more steps. Our evaluation underscores that even in domains where the premise order should not matter, it does influence LLM reasoning. This suggests that LLMs prefer reasoning in a linear, left-to-right fashion, likely due to their auto-regressive design or biases learned during training. Addressing the premise order effect in future training and modeling efforts remains an open challenge. In the benchmark section, we highlight the challenges LLMs face in logical reasoning, particularly with long proofs and multiple deduction theorems. We focus on a specific problem space from simple logic, involving propositional logic problems with definite clauses. Each problem consists of a set of true facts, a set of rules in the form, if X, then Y, and a conclusion that must be proved true. Unlike simple logic, which treats the problem as a binary classification task, our benchmark requires a completely valid generated proof for a prediction to be considered correct. We created variants of each logical reasoning problem with different premise orders to isolate the effect of order on reasoning. We categorized these orders based on their Kendall-Tau distance to the forward order, where premises are presented in the sequence they are applied in the proof. This setup allowed us to systematically evaluate model performance across various premise orders, revealing significant differences in how LLMs handle these tasks. We generated a comprehensive benchmark of 27,000 problems, offering a detailed look at how premise order and the presence of distracting rules affect LLM reasoning performance. Section Summary. In this section, we explore the impact of premise order on large language models, LLMs, in reasoning tasks. We find that while humans are not significantly affected by premise order in deductive reasoning, LLMs perform best when the premises are arranged in the same order as in the ground truth proof. Different LLMs show preferences for specific premise orderings, with some achieving better performance when the order is reversed, indicating a significant influence of premise order on LLM reasoning. Section: RGSM for mathematical reasoning. In this section, we explore the impact of the order in which premises are presented on mathematical reasoning. To do this, we created the RGSM dataset, which is based on the well-known GSM-8K dataset that consists of grade school math word problems. Our process began by selecting problems from the GSM-8K test set that had at least 5 sentences in their descriptions. We then eliminated any problems where rearranging the sentences would change the correct answer, such as those that describe events in a causal sequence. For the problems that remained, we kept the final sentence in its original place but rearranged the other sentences in a different order. We made minor edits to ensure the sentences still made grammatical sense. To help with this task, we developed a simple method to generate all possible sentence orderings for a problem until we found one that would likely cause a language model to make a mistake, yet still preserve the correct answer. This method was used to guide our manual rewriting of the problems. In the end, our RGSM benchmark included 220 pairs of problems, each pair consisting of the original problem and a version with the sentences reordered. Despite most problems in the RGSM having only 5 sentences and none having more than 8, we found that language models performed significantly worse on the rewritten problems. This suggests that the order of information can greatly affect a model's ability to solve math word problems. For example, in one case, the correct solution to a rewritten problem required referring to the second-to-last sentence rather than the second sentence, which was a departure from the original problem's logical flow. For our experiments, we tested the effect of premise ordering on several advanced language models, including GPT-4 Turbo, GPT 3.5 Turbo, PaLM 2L, and Gemini Pro. We used a method called greedy decoding and set the temperature parameter to 0, which means the models would choose the most likely next word without randomness. Our tests did not include any additional instructions for the models, except in cases where we were specifically testing logical reasoning. In those instances, we included a prompt asking the model to explain which premise it used at each step of its reasoning. Our findings showed that all the models performed best when the premises were presented in the forward order, which is also how humans typically prefer to receive information. However, as we increased the number of rules in a problem, the performance of the models dropped more significantly when the premises were presented in a non-forward order. This effect was especially pronounced in models with weaker reasoning capabilities. For instance, changing the order of premises could cause the accuracy of Gemini Pro and GPT 3.5 Turbo to plummet from over 65% to below 25%. We also looked into how the models handled distracting information. Without distractions, GPT-4 Turbo and PaLM 2L performed quite well, but adding irrelevant details made the task much harder for them, further highlighting the importance of premise order. Our error analysis revealed that the most common mistake made by the models was fact hallucination, where they would invent facts not present in the problem to try and complete a step in their reasoning. This issue became more severe as the premise order deviated further from the forward order. Overall, our research underscores the significant impact that the order of information can have on the ability of language models to solve mathematical word problems. Section Summary. In this section, we construct the RGSM dataset to investigate the impact of premise orders on mathematical reasoning beyond logic. We create pairs of problems by rewriting the problem descriptions with different sentence orderings, revealing that LLMs struggle more with alternative orderings, even when the original problem is correctly solved. Different LLMs show varying sensitivities to premise orders, with forward order generally yielding the best performance, while backward order is preferred by some models but not all. Section: RGSM for Mathematical Reasoning. In this section, we discuss our findings on the RGSM for mathematical reasoning. Our table showcases the overall results, highlighting that all large language models, LLMs, show reduced performance on RGSM. We note that the original GSM-8K problems might not always be presented in the most ideal manner, leading to instances where manually reordering the problems helps the model solve them more effectively. Therefore, in our table, we also include the accuracy rates for each LLM when tackling problems with their original descriptions. Our findings reveal that all LLMs struggle with at least 10% of the reordered problems that they could initially solve, with this performance drop being over 35% for GPT 3.5 Turbo. We further break down the problem complexity by examining the results based on the number of reasoning steps required and the number of sentences in the problem. As expected, we find that the accuracy of proof suffers for problems that demand more reasoning steps and contain more sentences. Notably, the discrepancy between accuracies on initial and rewritten problems becomes more pronounced with an increase in reasoning steps and problem length for both GPT-4 Turbo and Gemini Pro. However, this gap remains consistent across different numbers of reasoning steps and problem lengths for PaLM 2L and GPT 3.5 Turbo. In our error analysis, we delve into those instances where the LLMs could solve the original problems but not the reordered ones. We categorize the common types of errors in a table. Similar to what we observed in logical reasoning experiments, the prediction errors in RGSM are mainly due to the LLM's tendency to use numbers in the order they appear in the problem text. The most frequent error across all LLMs is their failure to account for temporal order. For example, we present a case where the prediction fails because some events described later in the problem actually occurred earlier. Another type of error arises when certain quantities are not specified in sequence, leading to the introduction of unknown variables for calculation. For instance, in the original problem, the number of each animal could be directly calculated from the preceding sentence. However, in the reordered problem, the number of gerbils cannot be directly computed without first calculating the number of fish, which remains unknown until later sentences are read. GPT 3.5 Turbo, in this case, incorrectly uses the number of rabbits from a previous step to calculate the number of gerbils, resulting in an error. This type of failure is less common with PaLM 2L but still represents a significant portion of prediction errors for the other LLMs. We provide more examples of model predictions in the appendix. Related to our work, several studies have identified various failure modes of LLMs, such as the reversal curse, distractibility, and limited logical reasoning capabilities. These studies show that including irrelevant context in a problem statement can significantly reduce performance on reasoning benchmarks, highlighting the distractibility of LLMs. This aligns with our observations on logical reasoning, where adding irrelevant rules not only worsens overall performance but also exacerbates the effect of premise order. The reversal curse offers another perspective on the order effect, demonstrating that recognizing A is B does not imply understanding B is A. While their work focuses on the order effect within a single factual statement, our research explores reasoning problems with multiple premises. The premise order effect on human logical reasoning has also been studied, showing that while premise order does not affect deductive reasoning, it can influence performance. For example, humans tend to prefer premises to be presented in an order that allows for immediate conclusions. Our findings suggest that LLMs share this preference, performing best when the ordering of rules aligns with the ground truth proof. Other studies have examined how premise order affects logical reasoning in humans, finding significant effects in solving certain types of problems but not others. Unlike these studies, our work focuses on problems that are generally easier for both humans and LLMs, yet we still find that LLM performance is sensitive to the ordering of premises. Lastly, Some prior works have shown that language models can understand texts with randomly permuted words to some extent. However, our premise order permutations, while not altering semantic meaning and remaining syntactically valid, demonstrate that LLM reasoning performance is highly sensitive to the ordering of premises, highlighting a significant area of vulnerability in current models.